All right, so this is part of chapter 16. We're going to talk about alcohols and the reactions that alcohols can undergo. So this whole chapter is based on alcohols. So the alcohols chapter and the previous chapter that we discussed will be on the exam. So that's what we'll see. That's electrophilic aromatic substitution, and now the alcohols. So there's a whole bunch of reactions that alcohols could undergo. Okay, we can turn an alcohol back into an alkene. We can turn an alcohol into an aldehyde or ketone. We could turn it into an alkyl halide. We can turn it into an alkane. We could turn it into an ester. We'll talk about tosylate and what tosylation is. It makes the OH a better leaving group than what it normally is. And we can even turn alcohols into ethers. So what we're going to do is you should be able to, okay, from Orgo 1 into Orgo 2 here, you should be able to create alkenes, alkanes, alcohols. We should be able to do all that, SN1, SN2, E1, E2 kind of stuff. And now once we create our alcohols from our alkyl halide, and we know how to do that, our alkyl halide substitution reaction, use an acid and water, if we wanted to turn it back into something, how would we do it? Okay, so let's start looking at our different reactions, and here's the reaction diagrams and the summary tables that we're going to look at the different reactions in here. It's a kind of a shorter presentation, only 36 slides, but at the end you should be able to turn your alcohols into anything that we had on that last slide. Okay, so first thing to review, okay, is redox and what oxidation is. All right, and reduction. So I can look at a reaction and to tell whether, and this is going to be important for those who have taken biochem, how to tell if I'm in a redox state. We know we could sign oxidation numbers, and we know that we can look at it and see if there's a change and all of that, but there is an easier way just to look at what's going on. All right, if I'm being oxidized, I'm either going to lose 2 hydrogens, I'm going to gain oxygens, or I'm going to gain a halogen. So if I gain oxygens, gain a halogen, or lose hydrogens, I've been oxidized. If I'm being reduced from reactant to product, I should gain hydrogens, lose oxygens, or lose halogens. If neither there's a gain or loss of hydrogen, water, or hydrohalide, then I didn't go through a redox reaction. Okay. So the first thing I want to talk about is primary, secondary, and tertiary alcohols. Now when we talk about primary, secondary, and tertiary, it means it's going to be a little bit different than with alcohols. With alcohols, okay, if I'm determining whether I'm primary, secondary, and tertiary, I look at the carbon that's attached to the OH and count how many carbons it's attached to. If that carbon's attached to 1, I'm primary. If 2, I'm secondary. And if 3, I'm tertiary. Now what the prime and double prime mean is that these are different carbon chains. Okay, they could be 1 carbon, they could be 10 carbons, and normally down here you would see, okay, you would see a little table, a little legend that tells you what each one means. All right. So, if I take my alkane and do an oxidation to turn it to an alcohol, if I'm a primary alcohol and I put it in the presence of an oxidizer, okay, and we'll talk about different oxidizers and things like that, I will turn a primary alcohol, will turn into an aldehyde. The thing about that is it's not well regulated, and my aldehyde will immediately go to a carboxylic acid. Okay? So once I start oxidizing a primary alcohol, I will get an aldehyde, but eventually I'll turn into a carboxylic acid. Key here, I'm being oxidized. Why? If we go back to our slide, I'm losing this hydrogen and this hydrogen in order to make a double bond. Okay? Right here. So I'm losing these 2 hydrogens. All right, the oxygen that's doing the oxidizing is going to form water. That's why it's in green. and I'm going to get an aldehyde. So a primary alcohol will turn into an aldehyde, which will immediately turn into a carboxylic acid, depending on what your oxidizer is. A secondary alcohol will turn into a ketone. Okay. And a tertiary alcohol will not oxidize any further. Why? Because there are no hydrogens to remove. To be oxidized, I need to remove hydrogens, add oxygen. There are no hydrogens attached, so therefore I cannot be oxidized. Now, what makes this interesting is the fact that a primary alcohol turns into an aldehyde or a carboxylic acid. When we drink ethanol, we have a enzyme in our body known as alcohol dehydrogenase, also shorthanded ADH. Alcohol dehydrogenase oxidizes our alcohols to turn them into aldehydes and eventually carboxylic acids. When we drink ethanol, ethanol is a 2-carbon primary alcohol. It will turn into ethanal and into ethanoic acid, also known as acetic acid, a carboxylic acid, which is a normal byproduct, and we get rid of it through our bodies. If we ingest methanol, and if you've been watching the news lately or have read the article, the FDA is recalling, or the CDC and the FDA are recalling a whole bunch of hand sanitizers that came out because they contain too much wood alcohol, also known as methanol. So if you drink it or you ingest it or it gets into your body in high enough amounts, methanol turns into methanal, which is formaldehyde, and you essentially are pickling yourself or, embalming yourself, and then turns into methanoic acid, which is toxic in even small levels inside the body. So this reaction right here is what your body is doing when you have a drink or 2 or 12 or 20. And because the ethanol is a toxin, and getting rid of it through the byproduct of acetic acid. So this is why the CDC, FDA are recalling the hand sanitizers. This is why you can't drink methanol. It's the same reason if you're drinking isopropyl alcohol. Why can't I drink isopropyl or 2-propanol? 2-propanol is going to turn into a ketone. We don't want ketones in our body. High amounts of ketones lead to ketoacidosis, things like that, and end up killing you. Okay? So we're tying a little biochemistry in right now with our primary, secondary, tertiary. But the key is primaries go to aldehydes to carboxylic acids, secondaries turn to ketones when oxidized, and tertiaries do not oxidize any further because they don't have any hydrogens. Okay. So secondary, like I said, become ketones. Reagents that are used, sometimes sodium dichromate in sulfuric acid. So if you see chromic acid, all right, potassium permanganate, things like that, those are strong oxidizers. Okay. It's a way, the chromic or dichromic acid test, chromic acid test, I should say, is a way to tell if you have a secondary alcohol, because there is a color change if I do have a secondary. So in a lab setting, when you go to take your labs, maybe you'll have this to test for primary, secondary, tertiary. You put a little sodium dichromate in there, or chromic acid, and you'll see a change from orange to green, and that'll indicate that you have a secondary alcohol. The green complex is going to indicate that you have or created a ketone in the process. The oxidation of primary alcohols. Now this is interesting. They go to an aldehyde, immediately to a carboxylic acid. It's uncontrollable. It is very hard to stop at the aldehyde. There is one reagent that will stop it, and it will only go to an aldehyde, and it's PCC. All right, pyridinium chlorochromate. PCC will stop the oxidation of a primary to an aldehyde. It will not oxidize an aldehyde to a carboxylic acid. It can't do it. So if you have a reaction where it's an aldehyde to a with PCC over the arrow, the answer is no reaction. you'd still have aldehyde. If it's a primary alcohol with PCC over it, it'll stop at the aldehyde. Any other oxidizer with a primary alcohol will give you a carboxylic acid. But PCC cannot oxidize an aldehyde, so it stops there. Okay. PCC can be used to oxidize secondary alcohols to ketones, but it does not react on, and this is PCC right here, it does not react. And if you took a biology class, pyrimidines and purines, you'll notice that this looks familiar. Okay. But it will not do aldehydes. It will not react with aldehydes. So, like I said, our tertiaries can't do any reactions to be oxidized due to the fact that they don't have any hydrogens. Okay. All right. What are some oxidizing reagents besides chromic acid and PCC? Well, you got Cr2O3 in a pyridine, which is known as Collins reagent. There's also, come on, Jones reagent, which is chromic acid and acetone. So you might just see the words Jones written over the arrow. As always, potassium permanganate, which we saw in the last slide, or the 2 presentations ago when we were doing reactions. Therefore, if potassium permanganate will do it, osmium tetraoxide will also do it. Okay. Nitric acid will work. Copper oxide at really high temperatures is used in industry. And there's something known as Swerin oxidation. I'm just throwing it on there. I'm not going to hold you to it, but it's on there. But the ones you usually use in lab are nitric acid, potassium permanganate, Collins reagent. Usually Jones reagents used a lot. Okay. Biological, I already talked about the reaction with ADH, alcohol dehydrogenase. All right, oxidizing agent NAD+, which is going to pick up a hydrogen. It's going to oxidize something. It's going to pick up a hydrogen. It's going to remove hydrogens from something, therefore oxidizing it. NADH then gets cashed in at the electron transport chain for ATPs. Okay, so NAD+, for that matter then, FAD 2+ or FADH+ is also going to be the same. I talked about ethanol and methanol already. And let's talk about here, ethylene glycol. Ethylene glycol, which is essentially antifreeze, oxidizes to oxalic acid, which is toxic. Ethylene glycol, and if you do this, this is a very horrible thing to do. If anybody in your family does it, try to talk them out of it. A lot of people, if they have feral cats or animals they don't want around, all right, then they leave out containers, bowls full of ethylene glycol, antifreeze. And the thing about antifreeze is it is very sweet to taste. So animals will come over and drink it. The thing is, it causes internal bleeding and your organs to shut down. And from what I've read in the past, it's a very painful death for the animals. Okay, so if someone chooses to do this to get rid of, there's more humane ways to get rid of your animals. Trap and release, trap and, put to sleep if you want to do it that way with CO2. But ethylene glycol should not be an option, in my opinion. That's just me. Just saying. I mean, I live in a more rural area. We've got animals running through here all the time. When my family comes up this way and they say, oh, there's a skunk digging under your shed or whatever, and it's going to make it collapse. Yeah, I just close the hole up. I make sure they leave, and then I close the holes up. I put, something in there that smells, ammonia rags or something to keep them from going back under there. But I'm not killing them. All right, I'm not putting anything out to kill them. So, but if anybody does ethylene glycol, not a good, in my opinion, not a humane way of getting rid of the animals. Again, very toxic. Something interesting though here is if you do have poisoning of methanol or ethylene glycol or something, and it's not to the point where you're dead already, they can treat you with excess ethanol so that the ethanol will get in there and mix together, and you'll get the byproducts that your body can pass safely. So that's kind of interesting. All right. So how about an alcohol acting like a nucleophile? How about we use out the alcohol being something that's looking for positives due to the lone pairs on oxygen, which is possible. The alcohol part is going to be partially negative, with the hydrogens being partially positive. So this is going to be partially negative right here, and a partial positive there, and kind of over here by carbon. And therefore, it has a lone pair, and it can be used as a nucleophile. Very possible scenario here. Now, the problem with it is it's not a great nucleophile. However, if I can remove this hydrogen, where the electrons come back right here and give us this full-blown negative charge, then we're going to have a really good nucleophile. But the alcohol could be used. Okay. So let's see what we can do with that. Okay. The OH is not a good leaving group unless it gets protonated. So if I wanted to add a carbon chain, all right, to be an electrophile, if I want a carbon to be attacked, being that it's partially positive, OH isn't going to leave. Okay, and this is where tosylate's going to come in and stuff. So this right here, okay, bad leaving group. So what can I do? Well, I can make it two hydrogens, all right, like so, bonded to an R group. Have that and have a positive charge, and now it'll be a better leaving group. Okay. So if I want to use the carbon as, or the alcohol itself, and specifically the carbon, as an electrophile, I really need that OH to be protonated to leave. Okay. So it could go both ways, but our other option is right here. Our other option is to use tosylate. Okay. Let me just get rid of our lines here, so we can see. Boom, 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 boom. Okay, so I can convert tosylate, good leaving group, to react with the strong nucleophile. Tosylate, I'll show you that in a second, why it ends up being a good leaving group and what exactly tosylate is. Right here, this is tosylate. Ends up being a good leaving group. This is tosyl chloride, to be exact. Come on, there it is. All right. So tosyl chloride, if I bond that sulfur to the leaving group, it's an even better, or to the alcohol group, it's a better leaving group than the alcohol or even a protonated alcohol. So what they say is you're tosylating it, or you're adding a tosyl group. All right, you're making an ester linkage. It is an ester, in case you don't see it, except it's a thiol ester linkage, or a sulfur ester linkage. You have a C bonded to an O that's bonded to an S that's double bonded to an O, and the leaving group becomes better. Okay, so if I have an alcohol and I wanted to act like an electrophile and add the carbon to a chain, I can do so by either protonating the alcohol or adding the tosyl group to it. So what can we make if we turn our OH into a protonated group? Okay, if we turn our OH into a protonated or tosylated group, the things we can do with this is we can turn it, if I have a straight up hydroxide, all right, I could essentially turn them into alcohols. So let's say I had water, I could turn it into an alcohol, right? If I had, or sodium hydroxide or something like that. Cyanide would produce nitriles, all right? Hydrohalides would produce alkyl halides. If I have an alk oxide, which we'll talk about, I can create an ether. Ammonia can create amines. And in the presence of a lithium aluminum hydride, I can make a alkane and do a little reduction reaction. And here's what they're basically showing you here. So if I tosylate something with a hydroxide, I'll create an alcohol. If I tosylate it with a cyanide, I'll create a nitrile, an alkyl halide, and again, all of this is on the slides. Okay. How about if I reduce my alcohols? All right. Reducing means I'm going to add hydrogens to them. If I want to reduce my alcohols, all I have to really do is put them in the presence of sulfuric acid. If I put them in the presence of sulfuric acid, I could turn them into an alkene. So alcohol with acid yields alkenes. The hydrogens from the acid are going to basically protonate here, electrons come back, and then we add the hydrogen here. So you got two hydrogens. One's going to protonate here, water's going to be removed. The other hydrogen from sulfuric acid is going to attach here, essentially, and you're going to create, or you can create your double bond, however you want to do it. Okay, so the OH is going to come off. You're going to have water. You're going to have a sulfate anion, which could pick up from the water a hydrogen. So you go back and forth here, where you're going to end up with water and a protonated, or a protonated water, also known as hydronium, or a refurbish of the H2SO4, or HSO4 minus sitting there. But either way, you're going to create an alkene. Okay. Electrons come down, form a double bond, and a hydrogen is removed from here to go back with the sulfuric acid. Okay, so hydrogen from here goes with sulfuric acid, turn into an alkene. Okay, oxygen is leaving. Okay, oxygen is leaving. All right. If I want to turn my alkene back into an alkane, we've already talked about this enough times that I just need to add hydrogen with our platinum or with palladium, okay, some metal catalyst to get us there, silver, all right, and so on. If we do this with an alcohol and then tosylate it, I can get it to an alkane after I create the tosylate with lithium aluminum hydride. So if you see tosylate and lithium aluminum hydride, know that you're going to reduce it back to an alkane. Alcohol plus tosylate will give you all you have to do is change the H in an alcohol in the presence of tosylate and make it OTS. So replace the H with TS. And then add lithium aluminum hydride to get you to an alkane. All right. What if I have an alcohol and I react it with an acid, okay, or a hydrohalide, okay? So either a strong acid like HBr, HCl, HI, or just a hydrohalide by itself. Well, that's why they show you the acid here, because that's essentially what it is. HBr is going to be in water. It's going to be H3O plus and Br minus. The first step is, since OH is a poor leaving group, our first step is for oxygen to take a hydrogen and become positively charged from our acid. Where's this acid coming from? HBr plus water. Okay. That's a terrible H, by the way. Let's do this. You think after all this time I'd have better practice with writing with, still don't though, plus H. That's a little bit better. H2O. Okay, that's going to create this H3O plus. Now the Br minus is going to sit there. This is a good leaving group. Okay, now it's a really good leaving group. It doesn't want to be there. It's going to take electrons away that way. Therefore, Br minus could come in and attack this as a carbocation. If I'm a third tertiary or secondary alcohol, when I do this reaction, it's going to go SN1, 2 steps, create the carbocation. If I'm a primary, it's going to do a backside attack, and all your rules for backside attacks. So, if the leaving group, if this is SN2, so let's say this is a primary, your product would look like this. It would have the reverse stereochemistry because it would have to do a backside attack. If it is a secondary or tertiary. Okay? You'll have an intermediate here in between here and here where there's a carbocation formed. The reason it doesn't do SN1 for primaries, again, is that the carbocation won't be stabled. Won't be stabilized, not stabled. Well, you're going to put it in like a horse stable. Stabilized, all right? Key is you're going to get an alkyl halide with the reaction of an alkyl halide or a hydrohalide with an alcohol. The process of how you're going to get there is all determined by what alcohol you have. Okay, same thing, HCl. Chloride is a weaker nucleophile. You may need a catalyst. So they usually throw in zinc chloride or something like that. It's also known as the Lucas test. Chlorine doesn't react as nice as bromine does. Okay, it's not as good as a nucleophile as bromine. However, you can do the Lucas test. You'll make up Lucas reagent, which is just zinc chloride with HCl. A primary alcohol will barely react and give you a result. A secondary alcohol reacts in 1 to 5 minutes, and a tertiary is almost instant. A tertiary alcohol will react with the zinc chloride Lucas reagent instantly. I know it says less than a minute, but if you ever do this in a lab. So if there's an alcohol lab or testing unknown lab that you're going to do for Orgo, what you would usually have is, a test for alcohols will be the chromic acid test. All right, to see, and then you could definitely nail it down if it's primary, secondary, or tertiary by doing the Lucas test. Okay. But it's the same process, just a little bit slower, different. Okay. HI doesn't react. Why doesn't HI react? Well, HI is a little out of control and a little hard to control. Control the rate of the reaction is what I mean by out of control. And by doing so, you may get an alkene instead of the alkyl halide. Okay. And again, problems, carbocation rearrangements and things like that. You can do something with phosphohalides, which is good for primary and secondary alcohols. You could even do something, SOCl2 works also. So if you see PCl3 or SOCl2 over an arrow, just realize that you're turning everything into an alkyl halide. Okay, you see an alcohol with SOCl2 above it or PCl3, realize that you're just turning it into an alkyl halide. Okay. And this is just showing the mechanism. Now this is going to be a multiple choice exam, so you're not going to have to really draw mechanisms, but you should know what your products are. And what the phosphorus does, essentially gets attacked and then causes a really good leaving group for the alcohol. So what it's really doing, I don't want to say protonate, but it's turning the alcohol into a positive and making it a better leaving group with the presence of phosphorus. So just another option to use instead of using acid if you didn't have acid available. And the same thing could work if you're going to use the sulfur. It kind of works like a tosylate since we're talking sulfur here. And again, makes it the alcohol a better leaving group. But really your finished product is adding the halogen that's there to the R group. Okay. All right. Dehydration reactions. All right. H2SO4, like I said, will produce an alkene. You could end up with a carbocation intermediate. Okay. So what you have to worry about during these, alkene to alkane transactions and transitions, I should say transactions. Transitions is the carbocation intermediate and rearrangement. Okay, so that's one big thing to worry about. Okay. Now, a Zaitsev product, that term means that you'll have a major product that has the most substituted alkene to it. All right, and what I mean by that is the following. Let's say, come on, draw. I have, okay, something like this. All right. And this is a CH3. And this is CH2. Oh, I didn't mean to do that. I should have just put a CH2. Let's just do this. We'll scribble that out. And go like that. Okay, and CH3 up here. So let's say that's what I have. Now I know that this OH group is going to essentially leave as a reaction, and this is going to come in. One of these hydrogens is going to come in to make the double bond. So this is going to leave. Now which hydrogen? So the question is, does one of these hydrogens leave and come in here? Or do one of these hydrogens come in here? So what is my majority product? And the majority product is this, and it's known as Zaitsev's product, because it's known as Zaitsev's rule, that says when a double bond forms, it's going to make the double bond with the carbon that's the more alkyl substituted. Okay, so you'll end up with something like this, not something like this. Okay, so this wouldn't occur. And that's what it means by Zaitsev's product. Because Zaitsev's rule says when a double bond forms, it's going to form the more alkyl substituted with the more alkyl substituted carbon. Okay. Now, that being said, let's do this here. Get my eraser out. Hello. There you go. All right. Just get this out of the way. All right. If you do your dehydration, okay, and it ends up being a bimolecular reaction, you could end up getting an ether when you're expecting just an alkane, which is good to know. Temperature plays a role. Okay? To do this dehydration with sulfuric acid and an alcohol, you want to keep your temperatures high. Above 150, they say 140, 150, 160, above that, you'll get an alcohol. If you do it at low temperatures and run this at low temperatures, you'll get an ether. Now, if you want to create an ether, that's great. Your alkene will turn to ether, or your alcohol will turn directly to an ether, and that's fine if that's what you want, but it's good to know that, hey, you might end up with a flammable product here, or an undesirable product, when you're shooting for an alkane or an alkene. Okay. At high temperatures, again, it's going to favor the alkene. Okay, that's why I said you want to stay above like 150, 160. They say 180 here. But if you want an alkene, high temperature. So what you might see on a reaction is alcohol, H2SO4, and like 70 degrees or 100 degrees. You should know your product's an ether. If it says high temp or like 200 degrees or higher, you know that you're going to get an alkene. If it says low temp, you know you're going to get an ether. So again, it's all clues on the reaction to indicate what your products are. And that's why I was saying, like, Orgo is, an interesting subject, but people make it a lot harder than it really needs to be. As long as you stay organized and look at the clues, you could kind of figure out what your product should be, and especially in a lab setting. You're reacting an alcohol with H2SO4 and you're looking to dehydrate it, but you're keeping the temperature low. That's not a good thing if, especially with, ether vapors, as long as there's heat around, the heat's hot enough to ignite the vapors, you could have a problem there. So this is showing the mechanism. Again, the sulfuric acid's there to protonate the leaving group to create our alkene. Okay. And here it's showing how at low temperatures what happens. It's protonated, but the alcohol then acts like a nucleophile and attaches to create your ether, which we don't want. Okay, so this up here is high temperature. Okay, so this up here is high temp. See if I can make my E a little bit better. And down here is low temp. So at low temperatures, the high temperature doesn't allow this to become a... There's enough energy, let's put it this way. At a higher temperature, there's enough energy in there to create the double bond. At low temperatures, there's not enough energy to create the double bond, and what happens is this comes in and does a substitution reaction and creates an ether. Okay. And this is showing the reaction diagram. I'm not going to hold you responsible for that, but it's showing the reaction coordinate. How about diols? Okay. A couple things about diols I want to point out is something called the Pinacol rearrangement, something called Pinacol, we'll talk about that, and acid cleavage. So let's talk about, we're not going to get really into diols a lot here, but Pinacol is 2,3-dimethyl-2,3-butene diol or butadiol. All right, this is the old way of naming it. Now you can name it butadiol if you want. Okay. If I want to dehydrate this with sulfuric acid, one thing that it could occur here, I got two diols. It's going to pick one of them, okay, and allow it to protonate and leave, which we're used to. So this will leave here. We'll have water over here as a byproduct, but again, organic chemists aren't worried about the inorganic products. We have our carbocation, but, what could happen? Okay, we've seen this before. What could happen is I have a carbocation here, but there's nothing saying that I can't do a carbocation rearrangement. And this would happen. Now, I know what you're saying. Why would I go from being a tertiary to a secondary? This is something that specifically happens with Pinacol. It specifically happens with Pinacol. Okay, or a diol that's similar to it. And we create something that looks like this, actually. So the bond, this CH3 moves over here where the positive is, and we create a double bonded O. It's just something interesting that could occur. Okay, I just want to point it out. And you end up with a ketone product when you go to do a dehydration reaction with sulfuric acid. So you do not end up protonating both OH groups and removing both OH groups. You end up with a ketone on one end and a methyl group on the other side where the other alcohol was. Okay. This will become more important in, and here's another diol again, cleavage of the thing with a strong acid. Here they're using periodic acid. Okay. And you can see you can create, actually in the acid you cleave here, just like you would in ozone. So a strong enough acid, just like in ozone, will break that up and create two ketones, or two aldehydes, or an aldehyde and a ketone, as we see here, depending on what the functional groups are. How do I get to this group? I could actually get to this using a strong oxidizer, like osmium tetraoxide in hydrogen peroxide, so really oxidizing there. And I can turn my alkene into this right here if I wanted to. We know that already, that across the double bond, we're going to add the two OHs. We really can also use this, right? We know that. Cheaper. Right? Potassium permanganate. I put a capital in there. I meant a lowercase n. That is awful. So do this, get rid of that, and get my pen back here. PNO4. We can always use. You can use Jones reagent if you wanted to, any oxidizer, but these will work because these will oxidize the double bond in both spots and put two OHs across, as we know. Okay, via the mechanism. If you don't remember that mechanism, go back 2 presentations and take a look at our elimination reactions, or not our addition reactions, that is. Okay. O3 going this way, ozone, will end up giving us this. So these two reactions from an alkene can get us to the same spot as if we had a diol already and we wanted to get there. So we've already seen those. How about esterification, making an ester? Now, if you take Orgo 1 and they have the lab, they usually do a banana oil or apple or something like that. I love doing the banana oil, making an ester. In order to make an ester, you need an alcohol and you need a carboxylic acid. The other big thing about your ester is it has to be a dry container. Whatever you're doing in your reaction flask, your round bottom has to be dried. So if you wash it pre-lab, make sure you dry it with, there's the air jets on the hood or something like that to dry it out and make sure there's no water. It's called Fischer esterification. You need an alcohol and a carboxylic acid. You could use tosylate. You could create sulfate esters. You'll see all these different esters in biochem, acetyl-CoA and those like that. Those you have to take it. Phosphate esters you see right in the DNA backbone. We'll talk more about that when we do the biochem section. So a carboxylic acid and an alcohol will give you an ester. Okay. It gives water as a byproduct. All right. You want to keep it dry. Too much water will make the reaction go in reverse. We'll talk a little bit more about that when we do carboxylic acids. Okay. Sulfuric acid is used as a catalyst, and again, the reaction is reversible. Make sure it's dry. Water is going to be driven off right here. H2O. Your ester linkage will occur. Your ester linkage occurs from, okay, the O of the alcohol with the carbon of the acid. So here's your acid. And here's your alcohol. Okay. Way you're going to name it. Again, this will be your chain. This will be the one that gets the O8 ending. Okay, so this would be an ethanoate. And this would be, your chain, which is attached. All right, we'll talk more about this when we do our carboxylic acids. But the key is you need an acid and an alcohol. So in theory, at home, if you did have sulfuric acid available as a catalyst, you can make an ester. And esters are known for their smells and their flavor. I mean, ethanol, which is readily available to us, is an alcohol. Acetic acid is vinegar. So in theory, if you had the catalyst sulfuric acid and were able to heat it, you'd be able to create ethyl ethanoate. I'm not suggesting you do so without a lab setting, but in theory, you can do it. Okay. Tosylate esters are just like they sound. You're using tosylate and an alcohol, all right, to create it instead of a carboxylic acid. Same process. Water is going to be driven off, and you're going to make an ester linkage to the tosylate group. Same thing with sulfate esters. Okay, the alcohol and the hydroxide, and you're going to create it with sulfate. Same thing can occur. Now, the cool thing about a sulfate ester is as long as there's OH groups, you can keep doing it over and over and over again. However many OH groups are present, you can keep going because the alcohol doesn't know the difference between this OH group and this OH group, so why wouldn't it do it to both? And it would do it to both. Nitrate, same idea, same principle. Where it's important, I didn't mean to click by that, glycerol. All right, this is glycerin, but glycerol as the alcohol. If I attach nitro groups to it, we get nitroglycerin. In biochem, and we'll talk about this again, this reaction with fatty acids, with carboxylic acids, which are longer chains, which are known as fatty acids in biochem, this will make a triglyceride. It'll take glycerol, those three OH groups. The hydrogens will leave. The OH groups of the fatty acids will take the hydrogen away with water and will create an ester linkage. And that's how we'll store fats in our body for later. Now, too many triglycerides start clogging up your bloodstream and could cause plaques and the stop of flow of blood to major organs, and specifically the heart, which we know as a heart attack. Nitroglycerin, though, however, all right, number one, explosive in high quantities, like a bomb, but also could be taken as a vasodilator. So if you have angina, aka angina, and there's limit blood flow going to the heart, and you start getting chest pain, you could take a nitroglycerin tablet, which would be a vasodilator. So all of this right here, you can see why the organic chemistry is important behind the biochemistry of stuff. Phosphate esters, as you can see on this phosphate, there's 3 different OHs, which means I can make an ester on each linkage. We actually make a phosphodiester bond as our DNA backbone. Okay. So we can make a phosphodiester bond with and here it is. Here's our phosphate group making the phosphodiester bond. Here's the diester bond. We'll do it right here. One right here. One right here with this carbon and that oxygen. Diester, phospho. And here's our phosphorus backbone. And we'll talk about this after we talk about amines and we get into our nucleic acids and things like that. All right, I had promised about alkyl oxides. Okay, so reacting an alcohol with a metal, okay, or a metal hydride. If I do this reaction, what I'll do is I'm actually protonating the alcohol, having the hydrogen leave. There's something known as Williamson's ether synthesis will allow us to make an ether. Okay. And there's the general reaction for doing so. And that does it for alcohols. Okay. So, again, this is chapter 16. They talk about alcohols, diols, and my camera is frozen. So they talk about alcohols, diols, and thiols in there. So you can talk about, it talks about tosylates and all of that in chapter 16. Okay. So I'm going to stop recording right there.